this example, we have a 200-gram mass hanging off a long string which is draped over a pulley and attached to a frequency generator which can operate somewhere between 60 and 120 hertz. We know the mass per unit length of the string. So if you did Physics 1021, you probably remember this from a lab. So this problem recreates something you would have done in the lab. So let's draw a picture of what's going on, and let's make a list of all the things that we know. So we have a table. On our table, we've got attached a pulley. Hanging over the pulley is a long string, and on this end is a frequency generator. So that's something that just oscillates up and down. So we've got our string attached to the frequency generator, and then the string falls over the pulley, and at the end of the pulley we've attached a 200-gram mass. Let's make a list of the things that we know. This hanging mass here is 200 grams. We'll write that down in kilograms. We know that the range of operation of the frequency generator is from 60 to 120 hertz. And what else do we have? The length of the string between the frequency generator and the pulley is 90 centimeters. So this bit of string here, I'm going to call that L. 0, and we'll write that down in meters. And the mass per unit length, that's given in grams per meter. I'm going to convert to kilograms per meter. And what we're asked for is what frequencies do we set on our generator to get standing waves on our string. We want to draw them and list the harmonic number. So we're asking for information about the standing waves. So let's think about some things we can sort out and where we'll go from there. So let's think about equations first. We know we have a mass hanging off this string. This is going to put tension in the string. So something we know is that the speed of the waves on the string is going to be given by the square root of the tension divided by the mass per unit length. Another thing we know is that if we have standing waves on a string, then the frequencies of those standing waves is given by the harmonic number m times the wave speed v divided by twice the length. What's important to know here? Our standing waves will occur between the two places where we have fixed ends. So one end that's fixed is going to be at the generator. One end that is fixed is at the pulley. So our standing wave is going to happen between here and here on this length of the string. This part down here, this is not going to have any waves at all. So what we'll do here is let's first find our V, and then let's use our V to find our frequencies. If we want to find V, we're going to need the tension. How are we going to find the tension? Well, one thing we know about strings, as long as they're considered ideal and massless, the tension through the whole string is going to be constant. So let's draw a free body diagram on our hanging mass. So there's our hanging mass M. The thing that's holding it up is the tension in the string. And the thing that's pulling down on it is the force due to gravity, or the weight. This hanging mass is hanging there freely, so let's write Newton's second law that says the sum of the forces in the y direction is the mass times the acceleration in the y. In the y direction, we have the tension points up, it's positive. The weight points down, it's negative. The force due to gravity, or the weight, is given by m times g. This thing is not moving up or down, so the acceleration is 0. M times 0 is 0. So the tension in the string is equal to m times g. If you're a symbols kind of person, you can leave it as symbols. If you're a numbers kind of person, you can put your numbers in. I think I'll go ahead and do the numbers. 0.200 kilograms times 9.81 meters per second squared to give 1.962 newtons. Okay, we've got our tension, now we can find our speed. V equals square root of t over mu. Again, you could leave this all in symbols if you wish to the very last step, or you can put in your numbers. I think I will go for numbers. So it's the square root of 1.962 newtons divided by mu, 1.51 times 10 to the minus 3 kilograms per meter. Remember, mu is the linear density, it's the mass per unit length. Put that through the calculator and we get 36.0 meters per second for the speed of the waves on the string. Okay, now we know V, so now we can turn to our frequency equation and find the frequencies of the waves on the string, remembering that the frequencies are going to have to be between 60 and 120. So let's write down that equation for frequency. Frequency equals, frequency of any given harmonic is m times v over 2l. M is equal to your integers 1, 2, 3, and so on. That's called the harmonic number. So that's one thing we know. The other thing we know is that our frequency has to be between 60 and 120 hertz. So there's our conditions. And L is the length of the vibrating portion of the string. So it's the length between here and here. The length is 0.9 meters. So let's see which frequencies are going to give us the answer we want. You might have an idea right off the bat. You might not. So let's just start with, if we're not sure exactly where to start, let's start with m equals 1. So the frequency of the fundamental, F1, is what we get when m equals 1. F1 is equal to 1 times V, 36.0 meters per second, divided by 2 times the length, which is 0.9 meters. So the fundamental frequency is 20 hertz. Is this an allowable standing wave on the string? No, it's not, because our frequency generator does not go as low as 20 hertz. Okay, our second frequency we could try, we probably know already, this one is not going to work out. We could try m equals 2. Two ways to do this calculation now. We can do F2 is equal to 2 times 36 divided by 2 times 0.9. Or we could remember that Fm is equal to m times F1. So this right here is the fundamental frequency. So any given frequency is the harmonic number times the fundamental. I'll go with this one just because I can do that math in my head. The other ones I would call it the calculator for. So M2 is 2 times F1. 2 times 20 gives us 40 hertz. Okay, that one is also not okay because our frequency generator doesn't go to 40 hertz. Let's try m equals 3. If m equals 3, then our frequency, F3, is equal to 3 times F1, which is equal to 60 hertz. That one is definitely allowed. Okay, how about m equals 4? We get our fourth frequency is 4 times F1 equals 80 hertz. That one is allowed. M equals 5. F5 is equal to 5 times F1 equals 100 hertz. That one's okay. You can also try m equals 6. F6 is 6 times our fundamental frequency to get 120 hertz. That one's okay. And then we can't go any higher because we top out at 120 hertz. So there's part A done. Which frequencies will result in standing waves? And then the next part is sketch each standing wave and list the harmonic number. Well, we've already got the harmonic numbers listed, so now let's sketch the waves. To sketch the waves, we have to remember what they look like for each harmonic. Our fundamental, if we were going to draw that, so F1, kind of covered up my space here, if m equals 1, our wave would go from our generator to our pulley in the simplest mode. That's what an m equals 1 wave looks like, and that one is not allowed. If m equals 2, we get the next standing wave on the string, which means we squeeze in another node or another half of a wavelength, and our wave would look like this. For m equals 3, so this one down here, for m equals 3, let's put an x by m equals 2 as well, just to remember that they don't apply. For m equals 3, we have to squeeze in another half of a wavelength. So there's our generator, there's our pulley. M equals 1 has a half a wavelength, m equals 2 has 2 halves, m equals 3 will have 3 halves. It will look something like this. Then m equals 4 will have 4 halves of a wavelength, or 2 full wavelengths. M equals 5, we get another half wavelength in there. And m equals 6, our final allowable standing wave, has one more half of a wavelength, so has 3 full wavelengths. Looks something like this. So this one is m equals 3, m equals 4, m equals 5, and m equals 6. So there's our problem solved.